So in this video we'll be taking a look at a selection of Arduino compatible microcontrollers which I've selected for some upcoming projects. Just to give a little bit of insight about what I've selected and why, and also give you a little bit of insight about where I'm coming from with this as well. So my background with microcontrollers is a little bit starting from something that isn't really a microcontroller itself. It's this Z80 chip here, made in Philippines. Quite interesting. So this one here, as you can see, it's dated 1983, which is pretty time accurate for a Z80. A lot of the personal computers boom was in the early 80s. Many of them were based on the Z80, and including one of the personal computers which I was using. Now, personal computers are not microcontrollers. However, in those early days, they were so simple that they were literally like a microcontroller. You know, they only had a very few number of components which equate, somewhat closely to a microcontroller, probably, but without the graphics capability and sound capability. But to program one of these micro processors, obviously you needed more than just a microprocessor. You needed to have some type of ROM for the program. You would need some sort of RAM. You would need some sort of I/O devices and peripherals, etc. So different to a microcontroller, you couldn't just run with the CPU, obviously. So my experience specifically was originally starting writing BASIC on these machines. Most of these machines were BASIC, but following that I started to write quite a lot of machine code, a lot of hand-assembled machine code. And actually I quite it's a frustrating process. Originally I was actually writing it on paper by hand and hand assembling a lot of those machine instructions and relative jumps and things like that. When you're a kid, it's it gets to your brain after a while. But the results were clear and obvious. These things, once you're writing in machine code, you're directly accessing the full speed and the full capabilities of the processor. And I remember I had written originally a game in BASIC, a Tron light bicycle game, and that game was slow. We're using the drawing interpreted engine of the BASIC, and it was pretty slow. So after learning machine code, I rewrote that in machine code, and it was literally, I don't know, maybe 50 to 100 times faster. And it was so fast that I actually had to slow it down. And so in normal speed, it was pretty lightning fast. And then you could press a button to go to lightning speed to try to get past your competitor, and it would double the speed. And it was that sort of difference. And so it was an eye opener for me just how much can be achieved when you're actually writing at that level. Moving on, however, later on in the early 90s, I ran into my first microcontroller, which is this little baby here. It's a ST Micro. I think it was originally a company coming out of Europe, SGS Thomson. So it's a group company from those days, but I think it's still called ST Micro today, with a lot of popular chips coming out, obviously, even today. But this was the first microcontrollers I've experienced anyway, and I think they're coming from as early as 90, 91. So you're looking at really start of 80s, where you really have mainstream 8-bit personalized use of microprocessors, and then you're talking about early 90s, where you're starting to get these single everything on the chip microcontroller. So everything on a chip we're really talking about. If we look at I think there's a diagram here. We're talking about here, input output ports, ADD converter, 64 bytes of RAM, wow, and about 4K worth of ROM, program counter, and active stack for calling and returning from subroutines, which was, pretty powerful in its day. It ran with a clock frequency of around about 8 megahertz, but it took around about 13 crystal clock cycles to actually create a machine cycle inside this machine. So you immediately have to divide that by 13, and then nearly every single command except for maybe 4 or 5 commands takes 4 machine cycles. So I think a single machine cycle is taking around about 1.6 microseconds or something like that, and it's probably taking quite a multiple of that to get anything done. So I remember I was doing a lot of development in video, working in PAL video, which is around about a line length of 64 microseconds. So you only literally had a couple of commands that you could do, maybe check what line you're up to and take some sort of action. And so you had to employ a lot of tricks to really make that work. The interesting thing, however, is that when you look at the data sheet here, there was two versions of this chip that I was using, by the way. This larger one here, which is has more I/O capability. But actually, if you look at the die is exactly the same. They're just not connecting the pins, basically. So it's a little bit of a tricky thing. The difference in I/O ports is 12 compared to 20, and otherwise it's pretty much the same chip as we know. But the interesting thing is, as you look at the data sheet, it's actually very similar to the data sheets you even see coming out more recently in the 2000s up until even today. Interrupts. So here we have the I/O ports, and there are 3 registers, similar to what you probably see today. It's usually probably three registers to control the mode, and you have the typical pull-up state or tri-state or output or sync state, etc., etc. You can, or interrupt assignments. All these things are done here with these control registers, just the same as what you see today. And here's a quick map of looking at how those configurations affect, and also routing to the analog to digital converter, etc. So, and this is the timer here. You can see with the prescaler and the counter. It's still 30 years later, and nothing much changes. But with that said, microcontrollers have changed in the sense that they've gotten a lot faster, and you get a lot more memory to play with, and there's a lot more peripherals coming in. So in this particular device, I believe there were versions of this device that it doesn't have a serial capability inherently in the device, because really there weren't that many applications that it needed to serve. I mean, I believe this series of chips eventually made its way into things like cars and manufacturing. So you had things like CAN bus and SPI and things slowly coming into it. But in these early days, the general purposes one, it just wasn't seen as necessary for the everyday user, I guess. And so they didn't have these features. So I think that's enough about that. I think I'm going to go back and have a look at a little bit of some of these projects that I did in the past in a little bit more detail, because they're interesting. But for now, I just wanted to touch on where we're coming from, and also just to say that I was writing assembly in Z80 already. This is a 91 Z80. Z80 already in the early 80s. In the early 90s, I was writing assembly for these guys here. Now I think you could write in C as well, but we're talking extremely small amount of program space, 4K of program space, and you're also dealing with 64 bytes of RAM and just a handful of registers. So once you get into writing in C and the compiler doing its thing, it's replicating patterns of things to achieve those C-type commands. You're never going to get a super high efficient usage of code space or memory space in that scenario. So for me, I never really crossed my mind that I'd be writing for this chip in C, even though probably some of my peers were doing it. I really like to write at that granular level and that machine cycle by cycle, memory byte by byte control level of coding. And to be honest, it was exciting and it was fun to be able to do that, to see that result. Up until then, I'd been doing a lot of electronics type work, analog and digital type, logic type controlling, and to be able to offload a chunk of work in a programmable sense in a single chip that you could plug into your board was, it was exciting, that's for sure. Let's move on. So what did I choose, and why did I choose it? So I'd made a decision early on to go with Arduino because I think one of my boys had originally been playing with them already, and the form factor was something that I was a little bit familiar with. It's a microcontroller in a sense, and so Uno is a bit of a no-brainer. There's a wide support for this. It's really the it's the bread of microcontrollers in my mind anyway. So, and this board is great because it can accept external voltages straight off the bat. It has internal regulators. It has all of these headers, which are great for quickly accessing and connecting to a breadboard or any configuration. There are a number of different shields that you can just plug straight in here and use it. So this Arduino Uno, I think it's still very relevant today, even though it's getting a little bit tired. I think it's getting to be quite an old chipset. So if we have a look at the processor, so the processors that we're talking here on this one is Mega 328P at Mel. Currently, I believe Microchips have purchased Atmel, and so it's now Microchip. And let's take a look at the data sheet quickly. 328P, 32 by 8 bit registers. That's a huge amount compared to the 6 or 8 that was in my old ST series. 16 MIPS at 16 meg. So that's again a multiple above what I was achieving with my older microcontroller. 32 kbytes of programmable ROM. That's nice. That's decent. Be plenty to work with there. And 2 kbytes of SRAM, and another kilobyte there worth of EEPROM, which is probably good for saving your user selected settings or runtime application settings that you want to save. That can be used between sessions. Quite a number of counters, PWM output, 6 of them straight out of the box. ADC, nothing new there. USART SPI, I2C, so good serial communications interface. On-chip analog comparator, that's quite interesting to see how that could be used as well. But, regardless, the chip is pretty capable. By more modern standards, it's looking a little bit tired, but I think for the most of your general purpose applications, this is a really good board to work with straight out of the box. I want to talk a little bit about this board quickly, as possible to talk about how it's structured. So the IOs, look, here, this is an image which is freely available online. If you do an image search, you'll find it yourself. And these images are really great. The people who make them are really, put in. I believe it's a lot of community, but probably businesses that do this. These maps really provide a quick view of what's where and what's available and how you can use it. And you'll see there's some restriction as to what inputs and outputs can be used in what formats, etc. But overall, it's pretty self-explanatory. The diagram here that I have here is pretty relevant, I believe, to this board I'm holding. There are a couple of different versions of this board, and I'll explain that in a second. But fundamentally what we have is a chip here, this CH340G, which is, as far as I know, a hardware, possibly who knows what's going on inside, but a hardware device which presents a USB interface and converts it into, what I would call an RS-232 RxTX port. So you can get onto your computer, open up a terminal, connect to this port, and send and receive data from this port. And it has all of those classic and typically highly unused little flags such as DTR, data terminal ready, RTS ready to send, I believe, etc., etc. I can't remember them all. And the interesting thing here is they're actually using the data terminal ready flag, which I'm sure that the program is accessing to reset the processor as well. So what's actually happening here is to program the processor, these Atmel 328 vanilla microcontrollers already have a preloaded chunk of code on them. And that chunk of code, when it boots up, it's looking for the signal, for an RS-232 signal or communication from the programmer, which is located on your PC, basically, obviously. So if it doesn't see that signal, then it'll switch to a vector, which is the start code for whatever program's been uploaded into it, or the user program component. So yeah, it's a, these boards are not clean in that sense. They are preloaded with a piece of code, as far as I understand it. And so when the programmer goes to reprogram or update it, it will set that this one here, this DTR line, reset the processor, and it'll switch itself into being in the program mode, and then the programming session will occur, and then it will release. And once the programming session is released, it will then flick into going and running the user program. Take a little bit more look at what are the bits on the board, because there's no mysteries here. I think it's all pretty straightforward. You'll see the two crystals. One of the crystals for the communication IC, and the other 16 meg crystal is for the processor itself. The external power has a 5-volt regulator on it basically, and if the external power is not provided, then I believe this op amp that they're using here is sensing that the input power is adequate or enough, and if it's not adequate, then it will switch in the 5-volt from the USB, so the USB can power it. And then there's also a 3.3 a 5-volt to 3.3 volt voltage regulator, which they're using here. And I've looked at this circuit diagram a couple of times, and maybe I'm not looking close enough, but I actually don't see on this board where the 3.3 volts is actually used for anything practical. It looks like it is an accessory voltage or something that can be used external if you're using a 3.3 volt device. So if that's incorrect, I'm sure somebody will comment on that. So other versions of this board, I have a board which I bought a while ago. This is actually a board I bought recently off AliExpress, and I think it costs, I don't know, it wasn't that cheap. I think it's about $5 or $6. But I have an older board which I bought for my son as a kit, in a kit, and this Elegoo kit, which is, I'm assuming, the same company that makes those 3D printers. The form factor is a bit different, and the layout is a bit different too. Fundamentally, the headers are in the same place, and this other header at the back here is the same, but these other subheaders are different. The crystal arrangement is different, etc. But the primary point is that they're using the same Atmega 328, but it's a DIP version, a dual inline pin version, as you can see there, elegoo.com. And the second thing to note about it is, and I had noticed this by doing a little bit of research. Focus! There we go. They have another microprocessor here, this 16U2, right? And there is no communications USB chip. So what's happening here is that this this microcontroller here has been programmed to behave exactly the same as a USB type interface and provide that communication link to the RS-232 communication link in the same way that the dedicated communication chips has. Now, I'm not really sure the exact reasoning why they switched to that, and it's quite bizarre that they have a high density form factor microcontroller here and a low density DIP here. It's confusing for me. I don't really know what the balance here, and the board is actually pretty nice as well, to be honest. But the net result is exactly the same. What's happening here is the same, except I'm assuming to save money, the use of this very tiny microcontroller is actually a lower cost option. And as far as I can see, no, I'm not right. It seems to be two crystals there as well to do this. Now, as far as the using this DIPS type chip, I think some of the older boards obviously originally started with that, so that's a continuance of that. But there are some upsides of having this here, because this board can be used as a programmer for these chips. So you can actually pop this off and plug it directly into your application and use this board as a programmer. So I think it's sort of a nice option, even though in reality I don't actually ever see myself doing that with this particular board. So let's move on. There we go. So the next up in my series of microcontrollers is this one here, and this is the Nano, or a clone of the Nano likely, and again we see a lot of similarities. And I had a look at the circuit diagram here. They are again using the 328 processor, and if we have a look at the circuit diagram, it's a little bit different in the sense that what is it different? it doesn't have the external power socket, but it does have the ability to have the 5-volt regulator, which is on the back here. But you'll notice there's no 3.3 volt regulator in the circuit diagram. However, this USB RS-232 conversion chip seems to be creating a regulator type capability. It's actually providing a 3.3 volt outage. And so again, the 3.3 volt is available on the header here for, I guess, for powering third-party 3.3 volt peripherals. So the key thing about this board is the form factor. You know, for me, the reason I purchased this is it was pretty cheap. It's about $2, I believe, this clone version. And the idea is that if you might be developing in here, but then your application, you might want to use something a bit smaller, and functionality is identical. Functionality-wise, it works exactly the same. So, you know, the form factor is obviously quite a different in that sense. So I thought it was a good option to have a few of these on board. And again, it's Arduino compatible out of the box. Something to note is that on the Arduino programmer, there's two options for the Nano: old bootloader and new bootloader. And funnily enough, this one here wouldn't program with the newer bootloader option, so I had to switch it to old bootloader, and then it programmed just fine. It seems to work just fine as well. And as with this clone board here I got from AliExpress, this is also from AliExpress. The what should be a FT232RL in the diagram actually is an unmarked chip, but you know, form factor wise and the way it's configured, you know, it seems to indicate to me that this is again a communications chip and not a microcontroller type implementation for establishing the communication from the USB through to the processor here. Okay, and just here as well, just on while we're sort of bouncing around here, this is a little shield I purchased, and I've done a few testing with this, and I'll feature this a little bit in a future video, and I'm sure many people have seen this before. But the idea of these shields is that, for those who don't know, is that the form factor is such that it just plugs in, and the drivers are pretty much available, and it's a nice neat little package, and touchscreen compatible, and away you go. So yeah, it's a really quick way to get some good functionality, even though it's a little bit on the slow side, to be honest, with this board here. Also to note on these headers, just while I'm on the topic of these headers, is that they're not actually aligned. So it's designed so you can't flip it the wrong way around. They're actually half pitch off, staggered. So, which is good for the inexperienced people not to get it wrong. I don't know how they'd get it wrong anyway. It's, you know, it's obviously different. But it's a bit of a pain in the bum when it comes to making your own boards to actually put in here, because naturally your pitch would be aligned, but you know, it's staggered, so it's a bit of a pain. So the next thing that I looked at was again something that I'd actually bought for my boy a while ago, and trying to figure out how these things all work. This is DigiSpark, I believe, and it's probably a DigiSpark clone if I understand correctly. It's something I've got, I think I got off Amazon, so, but just because it's off Amazon doesn't mean it's not a clone, I guess. The chip, as we can see here, we can see what's on that board. We have the AT-Tiny 85 microcontroller, and prominently we have a very big 5-volt power regulator, so you can take external power in and use that. I don't know why they put such a huge power regulator on it. It seems like overkill to me, but you know, especially when you look at the size of the power regulators on some of these other boards, like the Uno itself. I mean, where's the 5-volt one? I guess that might be it there. It's pretty tiny compared to that monster there. So anyway, mysteries. So look at the microcontroller itself. The 85, 8 kilobytes of programming flash, which is a pretty big downstep compared to the 32 kilobytes we have with the 328, and 512 bytes of SRAM, and again, you know, a quarter of the 328, but it's still 16 meg. Pretty much out of the box. It does have some timers and a lot less actually, but it does support SPI and I2C type interface, and I believe it doesn't support RS-232 type standard serial communication out of the box. That's something that I believe Ben Heck was harping on about, and he said that you needed to program it yourself, and so I find that a bit surprising, but if that's the case, that's weird. But this chip itself is, as I get to the point, it's pretty quick. I believe it's fundamentally as fast as the 328. The programming capacity is not great, and the 512 bytes is really not great either. But I think for the scale of the chip, it's probably adequate. Even though I say that, I've actually done a little bit of testing, and I do find it a bit restricting, and I wish it was a bit of a more powerful processor. So in this form factor here, the way they make it work is, again, they need a bootloader, something that talks to the programming software on the computer to write the information in here. And as you see, we have the ability to plug on the USB, but there's no communications IC. There's no dedicated communications IC, and that's a problem basically. So the way this actually works is that they've actually programmed the USB communications behavior into the software in the bootloader, as well as the programming behavior. So you actually have a much bigger, effectively, demand on the bootloader, in a sense. And given that you have a lot less ROM to deal with, it's more of a burden. In the Uno case, I believe I saw it's around about 512 bytes for the bootloader that's on here, and that's because obviously it's not having to behave as a USB host. But for this one here, it has, I believe it's around about 2K out of the 8K is consumed by the bootloader, and that's a lot, and that's a huge burden actually. And the behavior is nowhere near as good as the Uno. When the Uno boots up, it checks pretty quickly, and it kicks off the bootloader and gets into the program relatively quickly. It's not that big a delay, but and once it's booted up as well, it then can use the communications device here to establish a serial transmission and reception to the computer as well. So you can get on a terminal and send and receive commands to the process through this communication path. But here, obviously, that doesn't work that way at all. There's no communications path naturally established, so it has to be programmatically, and so therefore it's not practical. So the way the bootloader goes is you hit the program button on the programmer. It says plug it in. You have to dash to plug it in. The minimalized USB host temporarily, I assume, boots up as a limited USB serial host, and the programming session occurs, and then it kicks it off. And the host, the bootloaders, when it's not actually being used for programming, when you just power it up, is actually pretty slow to get to the stage of running the program. I find the delay to be quite long. And to be honest, I actually just find the whole bootloader implementation on this form factor to be quite unusable. So for me, this is not a practical something to use. I mean, it's nice to plug in and see the blinking light and do a few bits and pieces, but once you're left with 6 kilobytes of usable programmable language, which is going to be heavily compiled from C, it's not a practical thing to be dealing with. So instead, I went out and got myself this. Come on, let's get there we go. Oh, it doesn't matter, it's sideways. So these are a surface mount version of the same chip that's on that board. Obviously I can't do anything with it just like that, so I wanted to figure out how to program it. And so the first thing I do is repackage it into this form factor. So you have effectively a tiny little microcontroller board. See, getting even smaller. And then to program it, I went ahead and purchased one of these, because I really didn't know what I was doing, to be honest with you. And what this is effectively, it's this without the chip. So you need to program the bootloader on there and then it will behave exactly the same as this, and you'll notice the tiny little voltage regulator, which sort of adds to the mystery here for this voltage regulator. Yeah, this, after sort of figuring it out and programming a bootloader in it and then trying it out and understanding what's going on, you know, I just, especially when you program it, you take it out, you put it into your application, and you have to wait for it to fiddle around while it gets over its bootloading session, and possibly putting junk on the buses while doing that. You know, going, this is just something that was not that interesting to me. So, well, it's a good experiment, and I know how it works. So the way that I'm actually programming these is by using the Arduino Uno as a programmer. So you can do that. And there's a lot of information on the web and YouTube that teaches you how to do this. But you know, for me, you know, most people will put it on a breadboard and plug the ports up and connect it and use it. But if you're doing a lot of programming, it's not the way to go. So instead, I made this little board here. Basically, it's just one capacitor. I think it's on the reset line. I think it says you need to have that, and then it just connects up to the appropriate ports. Necessary lines to do the programming, so power and the necessary ports to do the programming. And so that just plugs straight in here. It's pretty hard to even get it wrong because it's designed to be that, and you'll notice that it's on a bit of an angle. And then the chip can just go straight in. And once you're like that, it's extremely easy to program using Arduino, or if you're working within the using the Atmel or microchip development environment, you can quickly set up a tool to program this chip via the Arduino, and that's, I've tested both those, and it's very easy to do. So this is a highly recommended configuration. You program it, you pop it out, you punch it into your application, and away you go. So you might be asking why I chose this form factor, considering that I'm just using a dip size header in any case. And the point was that these are actually a little bit cheaper. And the second point was that, you know, in my mind, if I was actually in the future making a very high density application, it's possible that I will, you know, make my own PCBs, and therefore, you know, really the form factor is the point of this chip. You know, you want to get it as small as possible. So the ability to have the smallest practical form factor for the typical user as an option is great. And if it's not, then it's very simple to change the form factor. You just get these little adapter boards and a bit of header strip, pop it on, and you know, you're back to a normal dip type chip. To facilitate some of the testing as well, I also made this little board, which just has a little power LED on it. Like that. And I've extended the power connectors here so that I can easily put some alligator clips on here. And the bus is just extended out like that, and a little bit of Kapton tape on the power connectors there. It's pretty straightforward. And so this effectively makes it behave a little bit like the Arduino Uno header board. I can program here, pop it off, and then push it into my application, and then my application could be connected to a breadboard or something else as I'm doing. So, you know, making the development fairly easy to program and test, program and test. So basically we only have two microcontrollers here. The AT-Tiny85, which is being used in the clean mode or the raw mode, nothing in there in programming, or can be loaded with a, I believe it's a micronucleus bootloader. And these standard Arduino type devices, which at this stage, you know, obviously there's probably a way to update the bootloader, and I haven't gotten to doing that, etc. But you know, fundamentally the ways you would use these is with the bootloader, and these are all based upon the Atmega 328. So beyond that, in the Arduino world lately, STM type cores, so the return of ST, for me that's for sure, have become available, and this is what has commonly been known as a blue pill. Processor is the STM32F103C8T, and this is a pretty interesting board. Now these boards also cost around about $2 in the current marketplace. And the I/O layout looks like this. So there's quite a lot of I/Os. It's a 3.3 volt board. That even so, a number of, or a good chunk of the inputs are tolerant to 5 volt logic inputs. And I'm assuming if you stick a 5 volt logic input on a 3.3 only tolerant input, it's probably going to fry it. So it's a little bit of a, got to be careful with that type of thing. But other than that, I think there's not really any great inconvenience with it being a 3.3 volt board. You know, 3.3 volts is probably going to work, you know, on the output side with any 5 volt type peripheral, because, you know, typically you see those devices triggering high status at the halfway point or a little bit above. So 3.3 volts is well above 2.5 volts. So, you know, I think there should be no reason for an output point of view you'd have a problem. And from an input point of view, as long as you're sort of careful and sticking to those 5 volt tolerant inputs where as need be, it's not a big issue. The processor, 32-bit Cortex M3 CPU core, 72 megahertz processor. I have no idea what that means in comparable MIPS, so I'm not going to go there, but I will say it's very, very fast. It's like lightning fast. This one has about 64 kbytes flash memory, which is, in a 32-bit world, is still not a fabulous amount of memory, but it's adequate, I would say. And then 20 kilobytes of SRAM is also adequate, I would say. It's not spectacular, but you know, for the price, I think you can't go wrong. If you want something that requires speed and doesn't require all that much sort of programming space, then this is definitely a great option. You know, all of the timers, peripherals, I2C, out of the box, serial capabilities, etc. You know, everything's in this board, so it's quite a nice little board. Now, the way the board is laid out is, you'll notice there is no extra chips on this board, different to the Arduino boards, and that's because the programming method is a little bit different. And if I understand correctly, obviously the board is not USB active when you just turn it on. There's no mode where you can switch it on and system. So there's no bootloader already built into this that just gets you connected to the PC. And to program it, you have to switch it into programming mode. Now, I guess once you switch it into programming mode, then it runs a different piece of pre-installed code, which doesn't activate the USB port or anything like that, but allows it to interact with the programming software through a direct RS-232 interface, and allows it to program the ROM, basically. And once you program the ROM, you can go to the run mode by switching this little jumper and putting it in there. So to establish the RS-232 communication with this chip, you need to get one of those chips, right? One of those RS-232 USB interface chips. And this is what this is. This is an FTDI 232. So it's an RS-232 converter. And it's basically the same thing that's on this newer Uno board. And so you wire it, so you connect it up, you put it in programming mode, and put the program in, and then put it in run mode, and away it goes. So from a bootloader capacity sense, when you're programming directly like that, it's not taking any capacity, and you're really operating at a raw level, and that works just fine. However, there is a bootloader available, and you can program it with the bootloader, and then it will behave through the USB nearly identically to the Uno, basically. And a lot of people will do that. And so once you do that, you never move this program line, because everything is programmed through the USB. Now, I'm not sure which way I'll go. I think if you're programming, I think I'll probably, you know, see how it goes with using the bootloader. But, you know, I've also done some testing without the bootloader, and you know, I think that works pretty good too. And, you know, I never feel comfortable about having that delay, that annoying delay when the bootloader sort of kicks in and then waits and then does its thing. So yeah, I'm a bit on the fence on this one. So one would think that after moving this pin and going to program it would work, but what I found with these boards is that the boot zero jumper here, it doesn't work on these boards that I got from China. And I actually found that a lot of people had the same problem. They don't work, and I'm not exactly sure what's going on with that. I mean, the chip looks genuine, but some people say there's some fake chips. I don't know. Is that fake? It just seems bizarre that someone would go to the effort of faking that. It just seems bizarre. Especially with the complexity of what's inside it. So the thing that I read online was that the hint that I got was that you should short out this R3. I don't like shorting out resistors. You never know what you're going to fry when you're doing that. So on the bottom of the board here, you'll see there's this R3, and they say short this out and it'll work. And so I did a little bit of investigation and I measured the state. And what happens is if you look at the circuit diagram here, you'll see the boot zero line and the boot zero line here as well. When you connect it into the boot zero mode, the 3.3 volt is applied and comes through this 100k resistor, and in theory should, I assume, pull it up to 3.3 volts and therefore the programming mode. But I measured this and I found that on the chip side of things, it was only getting to about 0.9 volts, so it never got above the halfway mark. It never got into the programming mode, and so that sort of was a bit of a trigger. And a little bit of calculation with the 100k here, which was originally here, and the 9 volts here at the 3.3 volts, was around about 40k internal pull down. So it can only be that in this chip on this line, on this boot zero line, there's a 40k pull down, which is creating that voltage division. So I didn't want to short it out, so instead what I've done is I put a 5k resistor here, and I had some 1206 surface mount resistors kicking around. Oh, that's very handy. And you can see my very nasty soldering job there. But by doing that, that pulls it well above the halfway mark, and this works fine, and I don't short it out, which freaks me out a bit. So yeah, this works fine now. So if you do come across these boards that don't work, my recommendation is not to short it, but if you can, put a 5k resistor in here, and Bob's your uncle, as they say. It'll be working fine. So for programming this, I made a few little bits and pieces. This little board here, which routes from this header here to the various pins that are necessary for voltage and programming on the microcontroller. So all you need to do is plug in the serial interface and plug in the board you want to program. You need to switch to boot zero mode. Write your program and then flick it back. Before you power off, you have to move this back apparently to the normal mode, and then reset, and away you go. Your program will run. And additional to this programming shield, I guess you would call it, I also made one more board the other day. I keep bending these pins when I pop this off. It's just another little board to make it act a little bit like a Arduino Uno header, because I find that quite convenient. Beautiful soldering job there, if I don't say so myself. So plug it in, and you have yourself a little Arduino Uno-esque development environment. So that's it. And just a quick bounce off the pricing. These Arduino Unos, I think they're about $5 to $10. I think you're pretty much paying for all of the infrastructure and size of the thing. These Arduino Nanos, you get them around about $2. And this Blue Pill, you can get them for around about $2. And originally I got these AT Tinies around about 50 cents, but they're around about 80 cents, and they're getting a little bit more expensive, which is not great. But if your application requires this form factor, it's definitely a good option. So simply, they're not expensive. They're pretty damn cheap, is what I would say in my words. the interesting thing is that once you probably populate this and mess around with this little ATtiny, in today's prices, you're probably around about $1. But this 32-bit blue pill is around about $2. So it's insane, right? I mean, this thing has got so much memory and so much power, and it's like, I don't know, 15 times faster than an Arduino Uno, at least. And you know, if your application is such that the form factor wasn't that critical. I mean, if your form factor was pretty much the same, I wouldn't even bother with the Arduino Nano. I'd just get the blue pill. I mean, they're pretty close. Just I think it's around about 20% bigger or something like that. But you know, 20% bigger, same price, 15 times the speed. You know, this is definitely the way to go. And it's got more IOs as well. And even when you're talking about this little baby here, you know, if we're talking about a fitted out cost of $1 compared to $2, you know, if the form factor, it doesn't matter if your application was really all that simple. If the form factor is similar and you have the possible need to have more requirement in the future for that implementation, then for sure you would probably give this a consideration. So for me, I believe that the blue pill is the go-to solution across the board in my mind as it stands today, and it's definitely something that I'll be focusing on. But at the same time, having these different known good, you know, well-supported implementations such as the Uno and the Nano, or even the ATtiny 85, you know, having these highly community-supported chips in your collection is definitely worthwhile, and I would recommend them. Now I have one more processor board coming, and that's the black pill, which has been released recently. And looking at the data sheet, this 32F411, the key point that I notice is really the programming flash. 512 kilobytes of flash is huge, and a really a big step up from the 64K available on the 103. So you know, if you have a seriously sort of user interface intensive or data intensive application, this is a great option. 128 kilobytes of SRAM, again, that's huge compared to 20 kilobytes. So this is really the differentiator for me. I also believe more IOs are 5-volt tolerant, if I understand correct, and it's a bit faster, 100 megahertz compared to 72. I think that's not the deal breaker, but it's nice to have. A little bit more speed never goes astray. I think one of the minuses that people have mentioned is that it drops from 2 analog to digital converters to 1. But it's a bit faster as well, so it's a bit of a plus-minus thing. I think if you were working on the premise that this was going to be for your user interface side of things, then it's probably irrelevant, I think, as well. So here we can see this is a diagram which I found on the internet. It says here all pins are 5-volt tolerant on F401. Pins 10 and 41 on F411 3.3 volts. So now we're seeing a switch in the layout that says, you know, you basically got 5-volt tolerance just about across the board. So that's a great change, I think. At the same time, they've actually managed to keep the layout nearly identical. I think this 5 volts here on the top right is new. It was originally ground on the here we see it's ground on the original 103 version of the board. So I don't have it here today, it hasn't arrived, but when it arrives I'll definitely be getting it out and giving it a run. My expectation is that the experience is going to be, you know, from a programming and execution standpoint, identical to this. So there's not that much to say about it, I guess, at this point. Alright, well I hope that's been helpful to someone. I know there's a lot of these type videos out there on the channel, but I you know, I think it's a good sort of reference, at least for me it was, to sort of consolidate you know, what I found when I was sort of looking for it. And again, you know, when I was looking for it, it's Arduino compatibility, it's you know, something that's popular and well supported, and you know, something that has a price factor, which means you could use it just about in any type of application without having to worry about you know, the cost aspects of things. And when you stop having to worry about the cost aspects of things, you know, obviously you know, it opens up new doors, and you can do more than you possibly would have done in the past. So it's going to be interesting. So yeah, well, I'll catch you next time anyway. Thanks.